Hello everybody, thank you for joining us today. You are part of the 420 people worldwide who have registered to view this webcast, powered by Yole Développement, dedicated to 3D and 2.5D TSV integration. My name is Faisal El-Kamasi. I'm a global sales support and coordinator for Yole Développement. Before we get started with this webcast, I would like to give you some information regarding the logistics. So you have the possibility during all the webcasts to submit questions. In order to do so, you simply have to use the box at the bottom of the screen where you can see Ask a Question. We will answer as many questions today as time permits, and for the remaining question, we will make following up via mails within a week. We'll do our best to do that. Concerning the materials and content, please note that the presentation is available and that you will have the possibility to download it in the materials section. You will also receive an email later after the webcast with a link to the recorded session. So today, Yole Développement, System Plus Consulting, and our proud sponsor, Broadpack, will share their analysis for you to learn more about 3D and 2.5D TSV integration. First, let's start with an overview of the related industry and the latest market and technology developments presented by Émilie Jolivet, Market and Technology Analyst at Yole Développement. Émilie, please.
Good morning, good afternoon. I am Émilie, and I'm here to give you an overview of the market and the applications of 3D TSV integration. We've done a webcast on TSV integration in January on this topic, and one can ask, why are we doing one today? Actually, because many things happened since January, and it's time to cover this topic. So, many things on the agenda. So for newcomers, I would like to start spending some time about definition and history of TSV integration. Then I will cover the application, specifically imaging and high performance with a focus on artificial intelligence. And then spend a couple of minutes on technology and specifically what we expect in the coming years. So what is 3D integration? So we consider a 3D TSV technology two things. When the device is completely stacked and interconnected through silicon vias. So in this case, we talk about 3D IC, and that's mainly memory and logic or logic and memory. And the second case is the 2.5D technology, when chips are assembled on a silicon interposer, and then in this case the TSV is also used as the electrical interconnection, but the second case covers the package of the GPU, CPU, stacked memories, and we will see there are more things in the future that will come or fall under this category. In terms of application, Yole has made a breakdown of three ranges of products. So there is the low-end product, mainly MEMS sensors and high brightness LEDs, where the driver is the form factors. There is the second case of the middle end that consists mainly in imaging, CMOS image sensor for mobiles, where the drivers are form factor but also the performance. It will be the first part of this talk. And the second part is about high-end or high-performance devices, where the driver is clearly the performance, and the applications are a bit more diverse, as we have the 3D stacked memories, silicon interposer, but also we expect soon the 3D system on chip and silicon photonics also in the future. So, what has made this 3D integration possible? Actually, TSV entered the consumer device more than 10 years ago with the VLS technology, and it has progressively penetrated more markets. and via middle have enabled large bandwidth DRAM memories, which is a hot topic now. So as I said, the learning curve was initiated in 2007, and now designers, foundries, and others have built a reliable and complete supply chain worldwide. In imaging, so TSV integration has played a major role in CMOS image sensor in smartphone evolutions, and mutually, CMOS image sensor have played a major role for TSV integration. In terms of wafer, in 2016, there was almost 1 million 12-inch wafer TSV wafers manufactured worldwide. So it's quite important for the TSV business. Even though a few years ago there was no use of TSVs, the introduction of the BSI stack technologies have fostered the adoption, and 3D integration is now essential, and there is no alternative now for the mobile. So to gain in performance and to answer the new requests, new needs of consumers, there were quite a lot of change in smartphone camera over the last years, and we expect more to come. To illustrate this year, Sony has launched a triple stack CES with a thin DRAM stack between pixel layers and digital signal processor. It was the first time that we see a 3-wafer stacked, and this evolution comes 1 year after Samsung introduced the copper cover hybrid bonding CES in its smartphone. In the next generation, we expect also new hybrid bonding, and most likely there will be a pixel level interconnect coming with a lower pitch. So as 3D integration is essential for CIS, many technologies are under development, and these millions of 12-inch wafers is likely to grow year on year at a quite nice pace. Other field of application that integrates copper, or let's say also hybrid bonding, it's the 3D imaging and sensing. So Yole will be dedicating a webcast on this specific new device on the 26th of September. But just to give you a brief view of that, so this new type of sensing will also fulfill the needs of the consumers through the smartphone, and the idea is to have an extra camera enabling the 3D imaging. And hybrid bonding will have also a role to play in this field. The second main field of the TSV integration now is the high-performance application. So you can ask, what is high-performance application? Actually, there are a lot, even though that was considered as niche market. Now there are some hot topics around, especially deep learning, artificial intelligence, and here TSV have a role to play. So because TSV device enables the transfer of large amount of data at high speed, get access to data with minimum latency, and store huge amount of data. So in high-performance business, we consider cloud computing, gaming, high-performance computing, networking in data center, and in the future we will add more augmented reality headset that will also require minimum latency and high-speed data transfer. So this slide was to help bridging the gap between the device and the market. So as you can see on the row, so high city and networking, more or less the data center field, require many 3D stacked devices like the 3D stacked memory cube, the silicon interposer, and 3D system on chip. But also there is the field of data analytics, which can take place in dedicated server or in big data centers, also very needing of high bandwidth. And there is the consumer computing that is more or less a new field of use of 3D stacked memories, or in general 3D stacked devices. But in this case, this year we heard about the iMac Pro from Apple using the AMD card based on HBM2 that Romain will introduce a bit later. We heard also about the use of the HBM1 in the game device Xbox One. And there is also the other fields of aerospace, defense, automotive computing, medical computing that require a lot of data analytics. And they need these new high performance TSV integrated devices. This slide was also to retranslate the number of TSV commercial launch that took place, that occurred over the last year. So as you can see, there were many devices launched recently. Even so, it started in 2011 with Xilinx, FPGAs from Xilinx. There was progressively the introduction of more and more complex and performant devices. So in 2014, there was the launch of the HBM1 and also DDR4 stack memories from Samsung and SK Hynix, which are the two main stack memory manufacturers. And it follows up with more commercial product like the Nvidia GPU Pascal and the GPU Fiji from AMD. So you see it's the very big name companies having now commercial solution using TSV, and we know that there will be more in the future because Nvidia and AMD are expecting, we expect new products continuously using 3D stacked memories. So as you may have noticed, there was over the last year many articles, many talks about artificial intelligence and deep learning. It's a hot trend. I won't read everyone, but I think it's quite interesting to ask why deep learning takes place now. It actually takes place for three reasons. Deep learning is a process that consists in educated machines. But for that, there was a first need of database to do it. And now with Facebook, Instagram, there is large available database of images. And it was the first step. The second one was more about the availability of the hardware offering large bandwidth as the type of device we mentioned previously. And there is the application side when there is now new needs in efficient data analytics solutions for the fintech, for autonomous driving, or just for consumer application in mobiles. Sorry, that was a jump. So there is indeed a recent opportunity because deep learning gained popularity along the last years. And as I said, the goal is to educate machine in identifying patterns, and it's now used mainly for language processing. But there is a lot of image recognition applications which are under development. So how does it work? It takes place in two steps. One phase that is called training, and it takes place in data centers, and it consists in really training, educating the neurons. So this part of the process requires transfer of data at high speed, so the need of the bandwidth is here. And there is a second state that is the decision or inference state that can take place or in a data center, or it can be embedded on a device, on a car, on a smartphone. This one is less demanding in terms of bandwidth, but those two steps are correlated, and we see now many companies making announcements on this process. So one can ask, what's the link between 3D TSV and the deep learning? Actually, that the capability of stacking, reducing the interconnection have helped to achieve the performance. Here are some examples of products which are used for training, and there is the Tesla P100 that Romain will show, but also now the AMD that we will also show. I wanted to highlight something that is a bit new actually in the semiconductor industry, is that what is at stake, the challenge of the high performance computing and deep learning is high. And now we see a slight motion, but quite interesting to consider, and that could have some consequences in the future. Right now, the big giant web companies like Google, Amazon, Facebook in USA, but also Tencent and Alibaba in China, or Baidu, they tend to have their own internal design, at least for the inference die. And they get involved from the very beginning, from the very first step of the design of the chip. And the second move actually is coming from card processor companies like Nvidia or AMD, Intel. They tend to go towards the system development, like Nvidia, which has launched a complete server dedicated to deep learning. So those changes are small or little change, but have to be considered because the involvement of Tier 1 will have some impact on the supply chain. In terms of market, what does it mean? Yole actually estimates that the size of the market in 2018 will be around 360,000 TSV wafers 12-inch. So it can be considered as a niche market, but when you consider the value of the wafer, whether it is an interposer or a memory with TSV inside, the value of the business is quite important. And you can see that we have a growth about 27% in the next 6 years. So it's a market that is that has taken off progressively. I wanted also to discuss a little bit of technology. I know that Romain will show you some nice pictures of high bandwidth memory, but just a status. So right now HBM1, HBM2 are available, and HBM3 is under development at JEDEC. There are still some discussion at JEDEC, but samples are scheduled for 2019. In terms of die partitioning, there are, as I said, there is the 3D system on chip now coming, but there is the die partitioning that also getting more interest, and Farhang will highlight the use of the silicon interposer. And to me, there is something that has to be considered when we talk about TSV integration, because TSV has a cost. Even though it brings performance, it has a cost. And now IDMs and OSATs are working on developing alternative technologies which should be low cost. And actually, there are a lot of development on a kind of high density fan-out, or let's say upgraded fan-out style technologies like Info or Focus, Swift. And there is the EMIB that is now the solution used by Intel for the FPGA strategic stem. So I just wanted to open the door to say, okay, 3D TSV technologies are getting interest. There is a market for it because it brings performance where no other technology could bring performance before. But there are also some challengers, and it has to be considered in the future. So thank you. I will let Romain show you nice pictures now.
Thank you very much, Emily, for this very interesting presentation. So once again, do not hesitate to ask questions using the Q&A button for the Q&A session that we will do at the end of the webcast. So we will continue with a presentation from Romain Fro, Chief Technology Officer at System Plus Consulting, with a presentation on 3D and 2.5D TSV in GPU Quad Technology Review. So please, Romain.
Thank you very much, Faisal. Hello, everybody, and thank you, Emily, also for the nice presentation. So today my presentation will be quite simple. In fact, I will show you two examples of GPU cards which have been released on the market quite recently. So one from Nvidia and another one from AMD. So in order to highlight the main components which are used by both players, and also to show the differences in terms of integration. So let's start with an example of Nvidia. So Nvidia released end of last year the Tesla P100 holding the Pascal GPU GP100. So these graphic cards are mainly made for data centers with some specifications which are highlighted on the slide here. So we received the board at System Plus during the year, and we realized the teardown in order to have access to the electronic board and to have access to the main GPU holding the memory with HBM2. So here you have pictures of the board showing the main integration. In terms of GPU here, we can see that the main package is a 55 by 55 millimeter package size, so it's quite a standard, in fact, in terms of size for such a larger GPU. Nvidia released two versions of the Pascal P100, one holding 12 GB of memory of HBM2 memory, and another one holding 16 GB of HBM2 memory. So as for the previous HBM product which has been released on the market in the previous years, the dies are directly stacked onto an interposer. So we have side by side the HBM stacks with the GPU on a large interposer, which is also directly integrated onto PCB laminate. In terms of footprint, we can easily understand that these such products able to save a lot of space at the board level. We already made in the past some comparison between solutions using DDR4 or DDR5 directly inside standalone packaging at the board level compared to HBM stack at the interposer level. So for sure it saves a lot of footprint, so 50% according to manufacturers. And again, in terms of performance, also it's much more better linked to the small connection between GPU and memories. If we have a look now at the supply chain of this processing unit here, so for the Nvidia Tesla P100, we can observe that TSMC is the main player, in fact, dealing with the integration of all of the silicon dies, the HBM stack, the GPU interposer. So what we can observe here at the component level is that we have a very large GPU, which is close to 600 square millimeter, using 16 nanometer FinFET process made by TSMC. Stacked just on the side of the GPU, we have 4 HBM stacks, each of them holding 4 GB of memory, with a total of 16 GB of memory for the complete structure. And as I said, there is also another version holding 12 GB. In this case, we observe that they are just using a fake HBM stack in order to hold the same structure with 4 stacked, because at the end we have a complete thinning of the HBM stack and the GPU in order to have the final thickness quite homogeneous. So on the side, on the right side of the slide, in fact, you have schematics showing the structure of the component with the estimated supply chain. So this schematic is not to scale here because you can observe that the DRAM stacks, the HBM stack, it's higher compared to the GPU, but in reality, of course, the GPU and the HBM stack share the same final thickness. So here we observe that the HBM stack is provided by Samsung, and the GPU dies, as I said, is made by TSMC with 16 nanometer FinFET process. Both GPU and HBM stacks are directly connected through a 2.5D interposer, silicon interposer, holding also the middle TSV. And this process, called the CoWoS, chip on wafer on substrate, developed by TSMC, enable TSMC to directly connect all of the die at the wafer level, and then at the end, directly connecting the final GPU, HBM, and interposer on a PCB substrate. So here we have a laminate substrate, which is quite impressive because it's all the 12 metal layer. Not so common for an advanced ICs. So we observed 10 metal layer in the past. So 12 metal layer for this substrate, it's quite impressive in terms of material. We assume that it is made by Ibiden, but maybe it's another player also which is providing this substrate. As I say, the process which is used for the integration is the CoWoS process of TSMC. So TSMC is providing different platform according to the kind of packaging and the kind of package size, die size, integration, and number of IOs. So here we have a package and die size which are really large. We have an interposer which is more than 1 square millimeter, 1,000 square millimeter, sorry. So the process which is used by TSMC here is the CoWoS XL due to the large size and the number of I/O, which is also really impressive at this level of integration. Regarding the memory, the HBM stack now, so we have HBM2 here, and as I said, it is directly made by Samsung. So Samsung is a provider of this HBM2 stack. So we have 4 stacks of 4 gigabytes. So we have for one HBM stack, we have 4 memory dies which are stacked with middle TSV and connected on top of a buffer die, a logic die. So here, in terms of number, Samsung estimates that there is more than 5,000 TSV per dies on each DRAM component. Now, if we compare with another provider of GPU this year, AMD released a very interesting graphic card holding the Vega 10 GPU. So we analyze the AMD Radeon Vega Frontier Edition this year. In terms of integration, again, it integrates HBM2 with 16 gigabytes also of capacity of memory. And compared to the solution used by Nvidia, you can see here that AMD only used 2 stacks of HBM close to the GPU. So you have a GPU here which is a little bit smaller compared to Nvidia with close to 500 square millimeter using a 14 nanometer FinFET process, and 2 stacks of HBM2 holding each of them 8 gigabytes of memory for a total of 16 gigabytes of memory. The final BGA package is a little bit smaller compared to the previous solution they released for the Radeon Fury X, for example. So you have a 47 by 47 millimeter BGA package. And if we have a look at the supply chain here, we can observe that the HBM stack here, it's also offered by Samsung. So previously, for the previous AMD solution, it was SK Hynix, the provider of the HBM stack. And for the GPU die here, it's GlobalFoundries, which is providing this 14 nanometer FinFET process. We assume that the interposer also could be provided by GlobalFoundries, but it's an assumption we made at this time. Maybe we'll have to confirm this later on. And the BGA package substrate here, it's a 10 metal layer PCB substrate. Previously it was provided by Ibiden, so we can also estimate that it is provided again by Ibiden in this case. In terms of final integration of the stack, the GPU interposer on top of the substrate, we assume that ASE is the main player holding this integration, but we also know that MCore has the capability to realize this, and maybe AMD is dual sourced this final integration with ASE and MCore for the integration at the substrate level. Regarding the HBM stack now, so HBM2 again for this one, but what you can observe here is that now they integrate an HBM stack of density of 8 GB, which is quite new on the market. At System Plus, it's the first time, in fact, we observed this 8 GB of HBM2 memory. So we have a stacking of 8 DRAM dies, each of them holding 1 GB of capacity. So in terms of integration, it's quite interesting because as you can observe, the final thickness of the stack is the same compared to a 4-die stacking. You can just observe that the final die is less thick compared to the previous HBM stacks, which were made by SK Hynix or Samsung with 4 dies. Again, the goal at the end is still to have the same thickness as the GPU in order to have a very homogeneous area and to green at the end. And so here, for us, it's the first time we observe this solution. We were thinking that SK Hynix were the main provider for AMD, but maybe SK Hynix it's not yet ready, in fact, to provide with a high volume production HBM2 with 8 GB capacity. So if you make a comparison between a solution which has been provided by AMD in the past, so for the Radeon Fury X compared to this new one, we can observe that, of course, in terms of performance, you have a 3 times more throughput in terms of teraflops. Again, in terms of integration, the package here it's a little bit smaller with the new version, 47 by 47 mm compared to 55 by 55 mm. But the GPU dies is also reduced with a die size of 500 square millimeter compared to 600 square millimeter in the past, linked to the shrink of the process, which is now a 14 nanometer FinFET process compared to a 28 nanometer process in the past. In terms of integration of the HBM memory, now AMD made the choice to have only 2 stacks of 8 GB, and previously it was 4 stacks of 1 GB. So we can observe that now the capacity is 4 times more important. And in terms of capacity per stack, the ratio is 8 times more important for the new HBM2, which is much more comfortable in terms of integration, in terms of footprint saving also, in order to have at the end a smaller component with a better performance. So to conclude on these 2 products, we can observe in fact that there is more and more products which are using 2.5D and 3D TSV each year. So we firstly analyzed the AMD Fury X 2 years ago. It has been released in 2015. So in 2016 also new products have been released, and now in 2017 also 2 new products are released on the market. So we can observe now that the TSV for interposer, for stacking of memory seems to be very mature, which is a good news for this industry. In terms of a standard for HBM, so HBM2 now seems to be the new standard for the advanced GPU card. For the 2 products we analyzed, Samsung were the main provider. Of course, we don't know if both players, Nvidia or AMD, plan to have SK Hynix in the roadmap also. We can just observe that maybe Samsung seems to be in advance at least for the 8 gigabyte stack of HBM2, and maybe AMD will diversify after that the supplying, the sourcing with SK Hynix and Samsung. So thank you very much. I give now the end to the next speaker.
Okay, many thanks, Romain. Many thanks for your presentation. So let's continue and end with a presentation from Farhang Yazdani, CEO and President of Broadback Corporation, on 3D and 2.5D TSV integration from imaging to deep learning. So Farhang, please.
Well, thank you so much for the intro. I am going to take about 10 minutes or so going over a few observations that we see across the industry here. So I briefly wanted to kind of talk about the rapid change in the market demand. This is something that Romain as well as Emily talked about it. I would like to talk a bit about the IP reuse. That's where the push is, and we see some changes in demand in this area. I'll then talk about very briefly about the heterogeneous element of the deep learning, the type of the options in terms of the packaging, etc. I will also talk about the substrate, the silicon as the foundation of such type integration, and I will wrap it up by talking about some of the key enablers and some key message at the very end. So as you've seen so far from the presentation from Emily, there has been quite a bit of change in the market. From our side, we see change in demand in the IP reuse, and meaning that once the IP chip design can be reused and integrated with other logics, and for that, the heterogeneous type integration is going to be the key enabler, and that's going to be needed. The other area that was just talked about was the AI, the machine learning, and the deep learning area. And for that, we see the demand for the HBM, the high bandwidth type of memory, the 2.5D 3D type integration, as well as fan out, or it could be just a traditional SIP. So it depends on the application. So for the high performance type application, HBM 2.5D is the route, and for other types, the traditional SIP would be adequate for that. So talking about the IP reuse, what is driving this request is really the cost reduction, and to be able to reuse the IP to connect with any type of core. So in this case, the customer would be supplying the core logic based on their own thoughts, and they should be able to easily connect to the peripheral IPs that is available off the shelf. So we call those the IP chiplets. Example could be PCIe, could be HDMI, could be, let's say, memory 5, etc. So the future of the SoC should be, by more of an assembly of this IP chiplets to the customer's core, and that's how things are happening. And but to make this a reality and to push forward, of course, a unified interface, a common interface is going to be needed. A kind of a standard that everybody can design their IP according to the standard, and that should take care of the integration among all the customers. And that work is ongoing. We are hoping within a year, or perhaps by end of the next year, we should have some form of a standard, and that everybody can agree to, at least to some point. And that should make the heterogeneous type integration more of a mainstream. The other market that it was just talked about, it was mentioned, was the neural network and the machine learning, deep learning type things. The way that we see it, there are three types of requests for that. It could be the simple network, where There would be just one single monolithic die that would go on a basic PVGA package, or just a flip chip BGA. That could be just a GPU die or a CPU or just FPGA. And that should get the job done. Or it could be more of a combination of the CPU, GPU, accelerator, FPGA, let's say some memory that would be integrated through a system in a package, more in form of the flip chip dies, and or it could be just a package on package, that you have the CPU, GPU on one package, and perhaps you got the also memory on the other package, and these are being stacked. Again, this is ongoing. However, the one that we see the demand and on the rise is more of the deep network for the 2.5D to 3D platform, as well as the HBM, where a lot of memory is going to be needed, and connected through a 2.5D and 3D type platform. Now, having said all of that, the question becomes the mechanism for connecting to these devices. What type of substrate and what is going to be needed? From what we see, silicon is really a multifaceted substrate. And for one thing, we can make it definitely with the high aspect ratio TSV. The processing has actually evolved for making the TSV, so a much higher aspect ratio is possible now, is being done. And once this capability is happening, we can make larger body size in terms of the interposer, meaning we can manage the coplanarity that goes on it, and that should make the ability to make a larger systems. The silicon can be, again, to be considered just as an interposer that sits between the die and the organic substrate, or just as a standalone substrate by itself. So you got two options here, how you want to package it. It could be just a multi-layer. We can have multiple layer RDL. We're talking about 3, 4, or even more available right now in the market. The sub 1 micron line spacing, that's again with 65 nanometer or lower, that type of line spacing is available. It's possible to make very high bandwidth, very wide bus connectivity among the devices. One of the most important features of the silicon that has been selected as for majority of this application is to consider the high thermal conductivity. Is a great conductor of heat, and that's one of the main challenges of the packaging, how to manage the heat. And this is one way to do it, basically. The high-speed signaling, there are many mechanisms to manage to transmit the high-speed signal through the RDL as well as through the silicon itself. So that is not an issue. The processing capability is out there to embed the passives, the caps, resistors, the inductors, either on the surface or embedding within the RDL. So that is also a very attractive feature that is available. The other feature is that the interposer, we can make it active. Part of it could be active, and for many applications, you might want to have some kind of a logic on the interposer as well, for whatever functionality or the demand. So that's going to be very important. The other thing is the wafer level fan out. We believe that the fan out capability is going to be very important for this market. The ability just to fan out the very fine pitch to a bit of a larger pitch for the ease of integration for other type packaging. So talking about the key enabler, we believe that the standardization on the chiplet I/O interface is the key enabler for the heterogeneous type integration, and that's going to be very important for the IP reuse. That way, everybody across the industry can share the IPs with the customer's logic. That's going to be important. mechanism for the non-good dies, or the chiplets in this case. So the IP provider should be able to provide the non-good of the chiplet. Interposers, whether you want to call it the substrate or the interposer, fine pitch with minimum at least, I would say, 2 layers of the RDL is going to be needed to manage this type of connectivity. The other thing is the fine pitch, I would say, bumping. The bumping houses, the capability to bump at a fine pitch is going to be important. The ability to do the fan out, the fine pitch fan out capabilities, that's going to be also important. I think this is the key important feature here. And lastly, the fine pitch die to wafer assembly capabilities, to be able to assemble the fine pitch IP chiplets onto the substrate or to the other wafer is going to be important. With that, the key message that I have is really to make the IP reuse move forward. The heterogeneous 2.5D fan-out platform is going to be needed for that, and that's what is happening as we speak. No doubt that the memory is the key player. In fact, the memory is one of those components is going to drive this type of I would say integration. And that for the deep learning as well as the AI, again, the heterogeneous 2.5D and fan-out packaging is going to be the key driver, and it's going to be needed. With that, I'm going to end my slides. I'm open to any questions. Thank you.
Okay. Thank you all for this relevant and interesting information. So we are now going to wrap up with a Q&A session. So we will answer as many questions today as time permits. We have about 10 minutes for that, and follow up via mails on the remaining questions. Okay, so I think the first question, Romain, we have a nice one for you. So what are the processes used for Nvidia and AMD interposer? So Romain, if you can help us for that to understand.
Yeah, thank you for the question. If I can answer quite quickly on this part, we just observed, in fact, that the processes are quite different for both solutions. So AMD, it's still using an interposer process with a backend online with a dual Damascene process, so it's copper metal layers. If we compare to the previous solution, now it's using 4 metal layers for the backend offline, 4 layers of dual Damascene copper, so it's quite interesting. And regarding to the Nvidia, for Nvidia here, the process is a little bit different because Nvidia, for this interposer, is using only 1 copper metal layer for the interposer and also 1 aluminum layer. So there is still 2 metal layers, but 1 copper and 1 aluminum here.
Okay, thank you, Romain. One question perhaps for Emily. What is the status of pixel level interconnect technology, meaning size of pitch?
So the status of the pixel interconnection, let's say pixel level interconnection, so that's under development. The commercialization is more estimated around 2019. Regarding the size of the pitch, that will be, around 1.2, 1.4 micron, most likely.
Okay, thank you. Another question, perhaps for you, Romain. What are the thicknesses of the DRAM dies in the HBM stacks?
The thicknesses here are they are quite close to 50 micron for both stacks. So the only the final stack thickness, in fact, compared to 4 gigabyte and 8 gigabyte are very similar in order to to be able to do the same thickness compared to the GPU. And so they are sharing the same thickness, close to 50 micron. But of course, for the stack with 4 DRAM dies, the latest one it's much more thicker compared to the other one.
All right.
So there is another one. Do you see any logic-to-logic die stacking using TSV? So currently that logic-to-logic is under development, but for sure it will come. There are big players working on that. So, or it will be like an active interposer as mentioned by Farang, or it will be more the 3D system on chip where we have a clearly die, which is partition. Then the two wafers are processed and then attached, connected with TSV. To our understanding, that's still under development, but expected yes in two years. Yeah.
Okay, thank you. And for the other question, we'll do our best to answer. So, okay, the webcast is ending. Thank you for listening to the full webcast. I hope you enjoyed it. As earlier said, you will receive an email that will include the recorded session. Please feel free to share the presentation with your colleagues that can benefit from the information that has been presented. You can also find our analyses and reports on more information on our website, imicronews.com. So thank you for joining us today. Do not hesitate to contact us if you have additional questions. For that, you can use the appropriate contact available on the last slide of the presentation. So have a good day. Thank you. Bye-bye.